Hi, Assalamualaikum. Good morning. We meet again in CHM477, Inorganic Chemistry. And today is my lecture 14. I'm going to cover valence bond theory, application to coordination compound. So if you can recall from my previous lectures, when we talk about valence bond theory, eventually we end up with hybridization. Yeah? Hybridization. So how do we apply hybridization in coordination compounds? We can do so. We can apply hybridization concept in coordination compounds in explaining some of the features or some of the observations of the behavior of coordination compounds. Now, features of coordination compounds that are not commonly found in other ionic compounds are their magnetism and colors, because as I was telling you earlier in a few lectures ago, that coordination compounds tend to have magnetism, either paramagnetism or diamagnetism, as well as display of good, beautiful colors. Now, coordination compounds are able to form complexes that have different geometries around their metal centers, depending on how many ligands are attached to the metal center. The geometry of the central metal will become different. Now we can describe the properties of coordination compounds using models that have been postulated by various chemists, mainly in the ways of why are certain geometries preferred? Why are the complexes colored, sometimes brightly? And why are the complexes behaving either paramagnetic or diamagnetic? How do we explain these observations? Now, let us first look at the valence bond theory, hybridization, to find some rationalization to these observations. Now, VBT has been extensively used to explain bonding and structure in the main group compound. For example, your ammonia would be sp3. Water would also be sp3, but it's bent. What else? Many things that we learned in our previous lectures. The concept of hybridization is a widely accepted concept, and it can be used to describe bonding in coordination compounds and complex ions. Now, to apply valence bond theory to our complex ions or to our coordination compounds, we can imagine that the ligand orbitals overlap with empty metal orbitals. The ligand orbitals overlap with empty metal orbital. If you can recall, if we talk about hybridization, for example, water, we treat the oxygen of water with the valence bond theory or hybridization, where the oxygen undergoes sp3 hybridization, and then that leaves us with two lone pairs of electrons and two sp3 hybrid orbital with only one electron each, ready for bonding with hydrogen. So when hydrogen comes in, the hydrogen will overlap, the orbital of our hydrogen will overlap with the orbital of oxygen, the sp3 orbital of oxygen, to make your bent-shaped water. So similar things can be applied in here. We can hybridize or propose a hybridization to the metal center, and those hybridized orbitals will then overlap with the ligand orbitals to make a covalent bond. Yeah, a covalent bond. The ligand, which is the Lewis base, now recall that ligands are any molecules or ions that have lone pair of electrons. Now, these lone pair of electrons are donated to the metal. So the ligand behaves as an electron donor, so it is a Lewis base, and the metal will accept these electron pairs donated by the ligand, and that will make your metal the Lewis acid. So when the metal accepts electrons from your ligand, it will form one covalent bond in the complex ion, and the complex ion is the Lewis adduct, is the product of the Lewis acid base interaction. Now, such a covalent bond in which one atom in the bond contributes both the electrons, it is called coordinate covalent bonds, or sometimes it is also called dative bond or dative bond. Yeah. Usually, typically when you have a covalent bond happening, for example, we take the water example just now, one electron from the oxygen will pair up with one electron from the hydrogen, and that pair will be shared between the oxygen and the hydrogen, making a covalent bond. So each one of the atoms involved in the bonding contribute one electron each. But for interaction between metal and ligands, the ligand provides both the shared electrons. Both the shared electrons come from the ligand. Because the electrons are shared, is still covalent bond, but we call it a dative covalent bond or a coordinate covalent bond, yeah? Because the shared electrons come from one source only, which is the ligand. Although you can name it whatever, once formed, it is identical to any covalent single bond. Now recall that the valence bond concept of hybridization proposes the mixing of particular combination of s, p, and d orbitals. Now you all know, you have answered my test. How do you define hybridization? And everybody answered, hybridization is the mixing of a few atomic orbitals to form a new set of hybrid orbitals. Yeah, a new set of hybrid orbitals. So mixing atomic orbitals giving new set of hybrid orbitals will also be happening in coordination compounds. Yeah, similarly for coordination compounds, the model proposes that the number and type of metal ion hybrid orbitals occupied by ligand lone pairs determine the geometry of the complex ion. So how that orbitals in the metal will hybridize will determine what is the geometry of the complex ion that you form. And it usually doesn't run away from the usual one. The coordination number of 6 is always octahedral. Yep. Coordination number of 2 will always be linear, but coordination number of 4 sometimes can be square planar or tetrahedral. Now, let us now discuss the orbital combinations that lead to octahedral, square planar, and tetrahedral geometries. Okay, let's go into octahedral first. Now, when you have 6 ligands attaching themselves to a metal center, you can treat the metal center to the valence bond theory treatment for octahedral complex, like is shown in figure 23.13 down here. Yep. The 6 lowest energy empty orbitals of chromium ions are 2 3d orbitals, 1 4s orbital, and 3 4p orbitals. Now, this is your 3D. There are The 3D orbital, there are five 3D orbitals, all degenerate, all in the same energy level. So we draw them as, I always like to call these terrace houses. Terrace houses they're like the houses built in, linked to one another. So 5D orbitals are always represented either as 5 boxes linked together or 5 lines attached to one another. The s orbital is always 1, so it's always one single box that is separated from the other. And then your p, you have px, py, and pz, 3 of them. So you have 3 p orbitals, 5 d orbitals, and 1 s orbitals. Now, chromium 3, yeah, chromium 3 ion is argon 3d 3. So you have to place these 3d electrons first. So you are placing 3 electrons in the d orbital in this way. You are placing them singly. You have to place 1, 2, and 3. You place them singly. You cannot say put this one and then another one pair up with it and then there's another one. You cannot do that because that will be violating the Hund's rule. Remember the Hund's rule, H-U-N-D? Yep. The electrons will occupy singly first. When the degenerate means at the same energy level, when the degenerate orbitals are full singly, then you start pairing up. That is to avoid a big repulsion between two paired electrons. If they don't have to, they won't pair up. Okay? So when you put 3 of these orbitals into your 3D, 3 of these electrons into your 3D orbitals, you are left with 2 empty d orbitals. Yeah? 2 empty d orbitals. They're not full. So because there are 6 ammonia, remember each one of the ammonia will be donating a pair of lone electrons to the metal. Yeah, remember ammonia has lone pair of electrons? If there are 6 of them, then the metal has to be ready with 6 empty orbitals to accommodate the 6 pairs of lone electrons from 6 ammonia. So the 6 lowest orbitals that is available for this chromium is 2 from D here, white, 1 from S, and 3 from P. So when these 6 orbitals, 6 empty orbitals hybridize, yeah, when they hybridize or when they mix, they make D2sp3 hybridization. So D2sp3 hybridization, where are they? Where is it? Yeah, D2sp3 hybridize. There you are. D2sp3 hybridized orbitals, and they are all in the same, they are all pointing from the middle of the chromium. Here is the chromium. 1 D2sp3, 2 D2sp3, 3, 4, 5, and 6 D2sp3 hybrid orbitals ready and waiting for 6 ammonia molecules to donate 6 pairs of lone electrons. Okay, are you with me? So one ammonia comes, donate the lone pair of electrons to this one at the top. So there is a chromium to nitrogen bond to the top like that. Another lone pair of electrons come from the second ammonia, making bond like that. The third, the fourth, the fifth, and the sixth. So D2sp3 is the hybridization of the metal center when it is bonded to 6 ammonia ligand. Yeah. So in the CrNH3 3 plus, the 3 plus is obviously the from the chromium oxidation state. In this complex ion, the d orbitals have a lower n value, obviously, because you have the 3d, whereas the s and the p are from the fourth series, lower n value than the s and the p orbitals, so the hybrid orbitals are called d2sp3. There will be a certain situation when we come to that. I will draw your attention to it when you can have sp3d2 situation, but that will be later. Yep, so remember when you have a coordination compound or a complex ion where the metal center is attached to 6 ligands, the hybrid orbital of the metal center is d2sp3, or it can also be sp3d2. Later when we see that case, I'm going to explain to you. Yep, d2sp3 for coordination number of 6, which is octahedral geometry around a metal center in the coordination compound or the complex ion. So I hope that is clear for you, the first case of octahedral. And I'm going to skip the square planar first. I'm going to go into tetrahedral geometry. I hope I don't forget to go back to square planar later. Now, tetrahedral complexes. Now, metal ions that have a field d sublevels such as zinc, which is zinc 2 plus is argon 3d10, often form tetrahedral complexes as shown in this picture here, 2.15, 23.15. For the complex ion zinc with 4 hydroxyl group attached to it, so this is called a tetrahydroxyl zinc, yeah. The valence bond theory proposes that the lowest available zinc 2 orbitals are 1 4s and 3 4p orbital. This is a mix to become 4sp3 hybrid orbital. Now, let me explain that to you. When you have zinc, if you can recall, zinc is in the last d orbital, if is on the 10th of your in the periodic table on the series of the 3D. So all the 3D orbitals in zinc 2 plus, they are full with the 10 electrons that is belonging to the zinc. Yeah. So again, you have the same situation here. You are lining up your 3D, 4s, and 4p. Yeah, you are lining up the 3D, 4s, and 4p. You're putting 10 electrons from the zinc 2 plus. So all of these d orbitals are full with electrons. So the next available 4 empty orbitals are the 4s and the 4p. So the 4s and the 4p orbitals, 1, 2, 3, 4, 4 of them will hybridize or mix to make sp3 hybrid orbital. Yep, sp3 hybrid orbitals, as you can recall from your previous lecture in VSEPR, is a tetrahedral arrangement. So you have 1, 2, 3, 1, 2, 3, and 4. 4 hybrid orbitals of sp3 waiting for 4 pairs of lone electron from 4 hydroxyl group that will act as ligands attaching themselves to the zinc. So these red electrons here are coming from the 4 hydroxyl group. One hydroxyl group give 1 pair to sit here, become like this, another pair, the third pair, and the fourth pair. So tetrahedral complexes have sp3 hybridization of the metal center. So that is nothing too unfamiliar to you, right? So I hope that's not a problem. Then the shape is very clearly tetrahedral, zinc with O with hydrogen there, zinc with O hydrogen, zinc, oxygen, hydrogen, zinc, oxygen, and hydrogen. Yep. So that is your tetrahedral. So whenever you have a tetrahedral complexes, you will know that the hybridization of the metal center is sp3. Then I'm going back to square planar. Yeah, tetrahedral is coordination number is equal to 6. 6 because there are 6 donor atoms surrounding the metal center. Now square planar is coordination number equals to 4, the same with your tetrahedral just now. Tetrahedral also is having coordination number of 4, yeah, because there are 4 oxygens donating to the zinc. Now going to square planar complexes. Now square planar complexes are very, very typical of any transition metal with D8 configuration, be it 3D8 or 4D8 or 5D8. 3D8 is nickel 2 plus, 4D8 is palladium 2 plus, and 5D8 is platinum 2 plus. So nickel 2 plus, palladium 2 plus, and platinum 2 plus, they have a huge tendency to form square planar complexes. And when we go into the next topic, you will also see that this always will be diamagnetic. So D8 will always have a tendency to become square planar and diamagnetic coordination compounds. Yep. So that is the nature. Yeah, that is the nature because of the energy dynamics in there. Now, in nickel CN4 2 plus ion, for example, the model proposes that 1 3D orbitals, 1 4s orbitals, and 2 4p orbitals of the nickel 2 plus will mix and form 4dsp2 hybrid orbitals, which point to the corners of a square and accept one lone pair from each of 4 cyanide ligand. So how is that explained? So we can read this later. I'm going to explain that through this diagram. So again, you see the now familiar arrangement of 3D, 4s, and 4p atomic orbitals. For nickel 2 plus, you have 3d8. So you are arranging 1, 2, 3, 4, 5, then 6, 7, and 8. 8 of the d electrons of nickel in this way. But for nickel, it is energetically more favorable for this unpaired electrons to pair up with this one. So it will pair up with this one to make this situation here. So the 8 electrons of your nickel 2 plus will fill up 4 of the d orbitals. And this is observed experimentally because nickel 2 plus is always diamagnetic. Yeah, it is always diamagnetic. So if it stays in this arrangement, you have unpaired electrons there, so it will become paramagnetic. So this is not what is experimentally observed. It's always observed that nickel is diamagnetic, so it is always the case of 4 electrons pairing up to make a diamagnetic compound like this. And after the 8 electrons pair up like that, you are going to have this orbital empty, that orbital empty, that orbital empty, and that orbital empty. So 1, 2, 3, 4. So this is DSP2. DSP2 hybrid orbitals 4 empty orbitals are ready to accept electrons, 4 pairs of lone electrons from 4 cyanide ligands. So there is one 4p unhybridized orbitals, but don't worry about that one. So you have dsp2 hybridization for all of your square planar complexes. Yep. Let's read this explanation. In the D8 configuration of nickel 2 plus, electrons in the half-filled orbitals, this one's here, yeah, pair up, and that will leave one of the 3D orbitals empty. This explanation is consistent with the fact that the complex is diamagnetic, which means no unpaired electrons. It requires that the energy gained by using a 3D orbital for bonding in the hybrid orbital is greater than the energy required to overcome repulsion of pairing this 3D orbital. It is a lot more energetically more favorable to pair up these electrons in that way. So the complex ion nickel CN4 2- as described by valence bond theory below is diamagnetic because it contains no unpaired electrons. So recall now your octahedral is D2sp3 or sp3d2 hybridization. Your tetrahedral is always sp3 and your square planar is dsp2 hybridization. Yeah, dsp2 hybrid. So that is the three geometries, common geometries of coordination compounds or complex ion around the central metal of transition metal complexes, which are octahedral, tetrahedral, and square planar, undergoing the treatment of valence bond theory or hybridization theory. So that wraps up my lecture 14 on the valence bond theory application to coordination compounds. Now, as you can see, the VBT, the valence bond theory, can explain the magnetism of your coordination compounds. Yeah, because you see here, your chromium 3 plus is paramagnetic with 3 unpaired electrons in octahedral geometry. Your nickel 2 plus D8 is diamagnetic through this treatment to get the dsp2 hybridization, and your tetrahedral complex of zinc 2 plus is also diamagnetic. All the d electrons are paired up, and the electrons coming from the 4 ligands sit in the sp3 hybrid orbitals. So magnetism can be explained pretty well using valence bond theory. However, the phenomenon of colors cannot be dealt with by this valence bond theory. We have to explore another theory to explain the fact that transition metals are colored. And that theory is called the crystal field theory, and I'm going to cover crystal field theory in my lecture 14. So until then, I'll see you later. Take care, keep safe, study well, and I hope you understand all my lectures today. Thank you. Assalamualaikum.